This is about instantaneous velocity and average acceleration. VINST and V average. And I'm not going to put the X subscript on here, but that's understood if we have an X-axis. So let's say that we had a situation where you were walking eastward at a constant velocity of 1 meter per second. And so we could represent your velocity as a vector that was pointing in the east direction, the positive direction, if we draw our x-axis in that direction. And we can say that this is 1 meter per second and it's constant. So if that were true, then we could plot your velocity as a function of time. There's t in seconds, and here's v in meters per second. And if we label these 1, 2, 3, 4, 5 meters per second, then you would have a plus 1 meter per second velocity, and it would be constant, and the v versus t curve would look like that. So this is the constant velocity. So in this particular case, with if we have constant velocity, then for this case, v instantaneous and v average are the same. And we also know from the area under arguments that we've given before that we could plot x versus t over here. So here's my x in meters versus time in seconds. 1, 2, 3, 4, 5 meters and 1, 2, 3, 4, 5 seconds. And I would get a x versus t plot that looks like this. So now let's assume a different scenario. Let's assume that you start at x equals 0 meters on a coordinate system, and that you start with 0 meters per second velocity, and that you increase your speed continuously by, so your v is going to increase continuously at a rate of 1 meter per second per second. In other words, you'll have a constant acceleration of 1 meter per second squared. And that being the case, then the v versus t plot would look like this. Time in seconds, velocity in meters per second for this new example. 1, 2, 3, 4, 5. And so 1, 2, 3, 4, 5. At t equals 0, you'd have velocity 0. At t equals 1, you'd have velocity 1. T equals 2, you'd have velocity 2 meters per second. So you'd get a straight line that looks like that. And the equation for that line is actually v is equal to 1 times t. And the coefficient multiplying t is the acceleration. So let me just highlight that. This right here is the acceleration, and it is constant. Okay, so if velocity increases continuously like this, what is the position, what's the displacement going to look like? And so we can plot that over here. So let's plot that right here. So here's t in seconds versus x in meters. And let's use a different scale here. Let's do this in twos. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. And so we know from the area under here. So if I go over, let me do this in a different color here. Let's say I choose magenta here. Let's say I go over some distance t, like this, and we know that the displacement from 0 to time t is the area under the v versus t curve between 0 and t. And again, since this is a triangle, the area under there is going to be equal to the base, which is of length t, and the height. So if I draw a little dotted line over here, this is going to be v at time t, which is just going to be 1t, times 1t divided by 2. So in other words, the area under is going to be equal to, for this example, 1/2 times 1 times t squared, or just to keep things simple, 1/2 times t squared. And that is the that gives me my position, which will give me my displacement. So using this now, I can make a table of t versus both v and x, and so let me do that here. So this is time, and here's my velocity, meters per second, and here's my time, meters. And so let's go from 1, 2, 3, 4, 5. Start at 0 here. I'll squeeze 0 in up at the top. So at time 0, my velocity is 0, and I'm at position 0 to start things off. 1 second later, my velocity is 1 meter per second. 2 seconds later, it's 2. 3 seconds later, it's 3. 4 seconds later, it's 4. 5 seconds later is 5, according to this function right here. And the formula for the position as a function of time is basically just 1/2 times t squared with the area under argument. And so if I put t equal to 1 in this formula, I'm going to get 0.5. If I put t equals 2 into this formula, I'm going to get 1/2 times 2 squared, which is 1/2 of 4, which is 2.0. And t equals 3 in this formula is going to be 3 squared is 9 divided by 2, which is 4.5. And 4 squared divided by 2 is 8.0. And 5 squared divided by 2 is 25 over 2 is 12.5. And so now we can plot that data on the x versus t graph right here. So here are my 1, 2, 3, 4, 5 points. And it's going to look something like, okay, this is 1/2 when t is equal to 1, and when t is equal to 2, it's equal to 2. And when t equals 3, it's equal to 4.5, which is about there. And when t is equal to 4, it's going to be equal to 8. And when t is equal to 5, it's equal to 12.5, which is right about there. And so you have a curve that goes somewhat like this. It gets increasingly steeper, and that's, as we will see, is a reflection of the fact that the instantaneous velocity is continuously increasing. So let's say we wanted to find the average velocity from 1 to 4 for this new scenario here. So let's say we had average 1, 4. So that we could represent by a line that went from this point to this point. This is the point corresponding to t equals 1. This is the point corresponding to t equals 4. And if I draw a line in between those two, let me make it a red line here, it's going to look like this. So the slope of this line, which is going to be this distance divided by this distance, that's a little right triangle here, this is going to be my change in x between 1 and 4, and this right here is going to be my delta t. The ratio of those two is the average velocity. So this is known as a secant line. The line between two discrete points on a curve is a secant line, and the slope of the secant line is the average velocity corresponding to the 2 points on the curve that the secant line goes through. And so what we would end up with in this particular case is we would end up with x of 4 minus x of 1 over 4 minus 1 seconds. And that's going to be equal to 8.0 meters. X of 4 is 8 meters minus x of 1 is 0.5 meters divided by 3 seconds, which is going to be 7.5 meters over 3 seconds. In other words, the average velocity between second 1 and second 4 is 2.5 meters per second. Okay, now to calculate the instantaneous velocity at time t equals 1, what we do is we consider v average from 1 to 1 plus delta t, and we let delta t go to 0 seconds. And so what we'd be doing then is we'd be keeping the secant line would be going through the point corresponding to t equals 1, but then as the delta t went to 0, this second point would be sliding down this curve and getting increasingly close to the t equals 1 point. And so you can imagine this line pivoting, and in the limit we would get a new line, which would be this blue line I'm about to draw here, which would be the tangent line at t equals 1. And so the slope for this line, is equals to the instantaneous velocity at 1 second. That's the key idea. And so we know from here that the instantaneous velocity at 1 second is 1. That's how we originally defined how the velocity would increase. And so this middle column right here gives us that instantaneous velocity. Okay, so that's the first point of the lecture here. Now let me do something else here, and let's remember from the definition for average velocity that v average between 0 and t is equal to the velocity at 0 plus the velocity at t divided by 2. But that's equal to v naught. Okay, the velocity at time t is going to be equal to the velocity at time 0 plus whatever the acceleration is times t. So we're generalizing this v equals 1 times t. We're generalizing that to v is equal to a times t, where this is the constant acceleration. And v0 plus at then gives me the velocity at some later time. So we can add those two terms together and divide by 2 to get my average velocity. That is if v0 plus v0 is 2v0 divided by 2 is just v0. And then a t divided by 2 is equal to plus 1/2 at. So that's my average velocity. And I know from the first kinematic equation that x of t is equal to x0 plus the average velocity times the time. So now we can put this expression in for the average velocity, and we will get x0 plus v0 plus 1/2 at, replacing this with that, times t, and what we end up with is x of t is equal to x0 plus v0 t plus 1/2 at squared. That's our second kinematic equation. So in words, the position for constant acceleration, the position at time t is equal to the initial position plus the initial velocity times the elapsed time plus 1/2 times the acceleration times the time squared.